system stability examples. Determine the stability of the following system. Let's look at the first one. Let's say we have a system given like this: d plus 1, d square plus 4d plus 8, y of t. That's equal to d minus 3 of t. So yeah, in order to find out the system stability, first what we have to do is we have to write this term, is d plus 1 d square plus 4d plus 8 in a characteristic equation. So here we use lambda instead of d. This is lambda plus 1, then lambda square plus 4 lambda plus 8. We equate that one to 0, find out the roots. So from this one, we can directly find this one, that is lambda, first root, that is lambda is equal to minus 1. And here we have two roots. When we solve the equation, we are going to have two roots. So this is a quadratic equation. We can apply this formula: minus b square root of b square, that is b square minus 2ab this is a, this is b, 4 times 8 square minus bc divided by 2a. Okay, this is the formula to find out the roots. From, if you solve this one, you're going to get plus, so minus a2. So if we apply these roots in the graph, it's first we have a negative one. It's a real axis and this is the imaginary axis. And for this one, we only have the real number that is at negative 1. Let's say it's here. Then here for this one, we have real and the imaginary part. Real part is negative 2 somewhere here, but the imaginary part is positive 2 and a negative 2. So let's say this is positive 2. Let's say this one is negative 2. We have these roots. But one thing is, all of the root are in the left here, left half plane. All roots are in the left half plane, therefore this is stable. If you watch my previous video, you know that if you have roots that is in the negative, like if the real part is negative, it doesn't matter where's the imaginary part. If the real part is negative, that is a stable system. If the real part is at 0, that is marginally stable. If the real part is at positive right hand side plane or positive, it is unstable. That's all you have to know. So here, if you look at this, all of them are negative. The real part is negative, so that's why this is stable. Doesn't matter what is imaginary part is. You have to just look at the real part. Is it negative, 0, or positive? If it's negative, that is stable. If it's 0, marginally stable. If it's positive, unstable. Now let's look at another. Let's say we have an equation given like this: d minus 1 d square plus 4d plus 8 y of t is equal to d plus 2 f of t. First we write the characteristic equation. Instead of d, we replace that one with lambda. So lambda minus 1, lambda square plus 4 lambda plus 8, that's equal to 0. This one we can directly find out. Here just equate that one to 0. So lambda 1 is positive 1. And to find out this one, we have to use this minus b square root of b square minus 4c, b square minus 4c. Yeah, that's the equation. Here is the 4c. If you look at this one and this one, it's almost the same. So if you apply that formula, you're going to get the exact same thing. Minus plus or minus j2. So lambda 2 and lambda 3 are minus 2 plus or minus j2. So now we can just draw the graph. The first lambda is at positive 1, so it's somewhere here. The lambda 2 and lambda 3, negative 2, one is positive to imaginary and the other one is negative to imaginary. So one is going to be here and the other one is going to be here. So here we have a negative and a positive. So what should we do? So first you have to look at, like, do you have anything in the positive? So if you have positive any value, that's automatically going to be unstable. It doesn't matter whether you have anything negative or 0, it's automatically unstable. And then let's say you have something here in the 0 and negative, then that's going to be marginally stable. So you can see, like, if unstable, that's the priority given the unstable first than anything else. And if you don't have an unstable and if you have marginally stable and stable, the marginally stable will be priority given. And if you don't have unstable, if you don't have marginally stable, then only that is a stable system. So here we have roots in right half plane. Therefore, this is unstable. Now let's look at another example. T plus 2, e square plus 4, y of t, that's equal to e square plus t plus 1, f of t. Let's write the characteristic equation. Lambda plus 2, lambda square plus 4. So if we equate this one to 0, it's going to be lambda is equal to lambda equals lambda 1. Lambda 1 is equal to negative 2. And lambda 2 and lambda 3, look at this, like if I equate this one to 0, lambda square plus 4 is equal to 0. Therefore, lambda square is equal to negative 4. Therefore, lambda is square root of negative 4. So that's going to give us a complex number. So that's a plus or minus j2, because we are square rooting a negative 4. That's plus or minus j2. So now we can go and draw the graph. First we have a negative value, negative 2 there. And then we have positive j2. So here this is 0, since we don't have anything here. So this is a 0 right here. Plus or minus j2. So this is going to be over here at 1. Actually 2 at 2. So j2. So this is going to be 2, positive 2 and a negative 2. But here you can see we have negative and a 0. 0 will be the priority count. 0 is marginally stable. This one is stable, but if you have marginally stable and a stable, the priority given to the marginally stable. So that one will be the answer. So roots on imaginary axis. Or roots of 0. That's all. Like the real thing that matters real value is 0. Or you can say real 0. Imaginary is positive to negative, it doesn't matter. So marginally stable. Let's look at the next one. Let's say we have this equation given: d plus 1, d square plus 4 square y of t, d square plus 2d plus 8 f of t. And again, write the characteristic equation. That is lambda plus 1, lambda square plus 4 square. Here lambda 1 is negative 1, lambda 2 and lambda 3. Lambda square is equal to, so the whole thing is equal to 0 first. And if you look at the previous one and this one, it's almost similar, like lambda square plus 4. But here we have square for that. So this is like exact same answer. Plus or minus j2. But the thing is, we will have repeated roots since we have square. So how do we draw this one? Let's look at this. We have a negative 1. That's somewhere here. And then we have, this is 0 since we don't have anything. So this one is j2. We have positive 2 and a negative 2. But this is repeated. So this is going to be second order. If you have first order, that's marginally stable. But if you have second order at 0, that's unstable. So this is going to be, we can say, repeated roots. On imaginary axis. That's unstable. It doesn't have to be imaginary axis, like you can have it 0, and if you have the second order, it's still unstable. So it's actually, if you have second order in 0 anywhere, that's unstable. And that's it. Thanks for watching. Don't forget to subscribe my channel. See you guys on my next video.